let's talk about the cross-validation error of the optimal, this maximum margin, this fattest separating hyperplane. And the result is going to be quite stunning, quite surprising. The miracle of the day. So the cross-validation error, ECV, for optimal, i.e. max margin / fattest separating hyperplane. Okay, what's the result we're going to prove? Okay, so the result we're going to prove is that the cross-validation error. Now remember what the cross-validation error was. Operationally, you remove a data point, you perform your learning, produce a final hypothesis on n-1 remaining data points, and test it on the left-out data point. And now you average over left-out data points. Okay. Now what and we showed when we talked about cross-validation that this cross-validation error, which we can operationally compute, is an unbiased estimate of the out-of-sample error, of the expected out-of-sample error when you learn on n-1 data points. Why n-1? Because you've left out a point, so you're only learning on n-1 data points, and the left-out point is a perfectly valid, albeit high variance estimate of the test error, of the out-of-sample error for that learning on n-1 data points. So E out of n-1, so the out-of-sample error when you learn on n-1 data points is related to the cross-validation error. This is an unbiased estimate of this guy. Okay, so if we can control, if we have a handle on the cross-validation error, we have a handle on learning, on the out-of-sample error. Okay, so here's the result we're going to prove. And this is a pretty interesting, stunning result. Miracle of the day. The cross-validation error for the optimal hyperplane, for this fattest hyperplane that separates the data, is at most the number of support vectors divided by n, the number of data points. Now, let me remind you, what was the number of support vectors? So we'll do this with a picture. So you've got some data. Okay, so some blue points. Okay. And you've got some red points. Okay. And you go and you run your algorithm, your optimal algorithm, the quadratic programming algorithm that produces the fattest separating hyperplane. Okay, and maybe it produces something like this. Okay, so it's got a margin, it's got a thickness. Okay, and you can imagine, you start at this optimal separating hyperplane, grow the cushion, and it simultaneously hits, blue points and red points, and that's where the cushion has to end. Okay, so let me box these blue points and red points that it hits. Okay, now those are what we call the support vectors. So we call these the support vectors. Okay. They are the important data points highlighted by this fattest separating hyperplane. But more importantly, okay, if you throw away all the other data, all you need to keep are these support vectors, and you will reproduce exactly the same optimal fattest separating hyperplane. So, summary, the final hypothesis does not change if you only keep the support vectors. These data points that are on the cushion. Okay. Now, as you generate more and more data, you're going to be generating points, okay, blue and red, and occasionally you'll generate a point that may be a support vector or maybe inside the margin, and in which case you will update the classifier. But most of the data you generate are, away from this critical region. Okay. And so what that means is that as you generate more and more data, the number of support vectors is staying approximately constant, and this n is getting bigger and bigger. And so this says that the cross-validation error, is dropping to 0 very rapidly. Okay. And, so that means that out-of-sample error is dropping to 0 very rapidly, okay, because the in-sample error is 0. Okay. So the in-sample error is 0, so the out-of-sample error is dropping to 0 very rapidly. In-sample and out-of-sample are getting closer. Okay. And what is really stunning about this result is that, it has no explicit dependence on the dimension. Okay. So there is no explicit dependence on the dimension. Now, it is true that as you go to higher and higher dimensions, the number of support vectors might increase a little bit. Okay, but as long as it's increasing very slowly or not at all, okay, with enough data points, your cross-validation error is under control. Your E out is under control. Okay? And that's all we care about from the perspective of machine learning, from learning from data. Okay? And it's independent of the dimension. This suggests that we can go to higher and higher dimensions and perform learning as long as the number of support vectors is under control. If we have enough data and the number of support vectors is under control, our out of sample error is under control. So let's prove this. Miracle of the day, stunning result. Proof. And the proof is not hard, even though the result is quite stunning. So let's imagine that when I'm computing the cross-validation error, so I leave out a data point, I learn, and then I evaluate on the left out data point. So let's imagine I leave this data point out. Okay, so that's not a support vector. Now, this is the critical point about support vectors, that I left out a data point that's not a support vector, which means I've kept my support vectors, which means that the final hypothesis hasn't changed. In fact, I could leave out all the other data, but I'm just leaving out this guy. So my final hypothesis did not change. So when I had all the data, with this final hypothesis, I separated all the data. So that means that this final hypothesis gets this data point that I left out correct, even though I left it out, because the final hypothesis didn't change. Okay. So let's summarize that discussion. The error made on a left out data point, so X, left out, that's not, so let's call this the error, the leave one out error, because I've left out that data point. On an X that's not a support vector, is 0. For the simple reason that the final hypothesis has not changed, because it's not a support vector. And it's only the support vectors that are needed to define the final hypothesis. Okay? So the final hypothesis has not changed, and that hypothesis classifies all the data correctly. So in particular, it classifies that left out point correctly. So the error that hypothesis makes on the left out point is 0. So I've gone through that argument now twice slowly because it's an important argument. Okay? The support vectors are all you need to reproduce this final hypothesis. Okay. Now, let's look at the left out error, the leave one out error, E leave one out, on a data point that is a support vector. Okay, so supposing instead that I leave out this guy. So I leave out this guy. Okay. Now, it's possible that the final hypothesis changes. Okay. It's also possible that the new final hypothesis will get this one correct. Okay, so you may predict correctly on this left out point and incur no error, but it's also possible that it gets this guy wrong. And you'll incur a misclassification error of 1. Okay, 1 error. Okay. So in either case, the error on this support vector, the leave one out error on this support vector is either 0 or 1, so it's at most 1. It can never be bigger than 1. So it's at most 1. Okay. And so let's see what the cross-validation error is. So the cross-validation error, ECV, is equal to the sum over your data points, little n equals 1 to big N, of the leave one out error for when data point xn is left out. Okay, and we take the average. Okay. Now, the non-support vectors contribute nothing to this. So this is equal to 1 over n, the sum over the support vectors of the leave one out for the support vector, x support vector. But that is at most 1. So this is at most 1 over n, the sum over your support vectors of 1. But this just counts the support vectors. So this is equal to the number of support vectors divided by n. End of proof. That's how simple the proof is. Okay. Miracle. We have bounded the cross-validation error in terms of the number of support vectors. And okay, there's the 1 over n. That 1 over n is coming from the fact that we are averaging the leave one out errors. Okay. But this result is quite stunning. It says that, we might be able to, control the out of sample error, okay, even in very, very high dimensions. All it depends on is the number of support vectors. Now, in practice, we can actually compute the cross-validation error, right? We just, leave a data point out. We only need to consider the cross-validation error for the support vectors. So we run the algorithm, find the support vectors, Okay, leave out each support vector one by one and see if they get classified correctly by the leave one out hypothesis. And we can actually compute this number and not get an upper bound. But the beauty of this upper bound, okay, is that it shows us what the cross-validation error can depend on. And if we have a control over the number of support vectors, the out-of-sample error is under control. More specifically, the cross-validation error is under control.